All right, today we're doing the behind the scenes of the space elevator calculation that we have kind of prepared. We're going to see if it worked out. Take it away.
Yeah. So I did this calculation for space elevator drift as the space elevator cargo container, whatever, is climbing the cable.
Okay.
And I want to see if our calculation is correct. So first thing, space elevator, this is what it looks like if we ever made one. Instead of like sending rockets up into space, we have this cable attached to the surface of the Earth that goes up to a space station at geosynchronous orbit. And the payload is this white thing with all this stuff on the side, climbing the cable.
Okay.
Much better way to do
Instead of
space
having
launch
instead
without
of having individual rockets that are trajectory, like you just send it up a cable.
sending up cable. Super easy. Of course, look how long this cable is. So ridiculous.
Yeah.
Uh, so one of the complications of this is this drift. If we go to the next picture, so this is like a more of a technical drawing, but still kind of cartoonish. Is ideally if we had the cargo or the payload climbing the cable, it would go vertically up, just up.
Okay.
Because the Earth is spinning and the cable is actually, if we got free motion, the payload will actually drift, in this case, to the west because of the Earth's rotation,
Oh, it's
which
like
makes
it's like
the cable go off.
you're saying ideally the cable should be straight up. That would be like the shortest distance
That's right.
straight up to the Earth, straight up from the Earth, but it's not like a rigid. It's a whip. Like it, and so because the Earth is rotating underneath the cable, that effectively, which I guess is the Coriolis effect, effectively that makes the cable deflect.
That's right. And so it's something that the engineers of a space elevator in the future would have to take into account. That as you climb, you're going to have this drift, and so you got to compensate or take it into account somehow. So this calculation I wanted to go see if I got correct or the idea correct was how much drift. If you climb at a certain rate or a certain distance, how much drift do you accumulate? So I don't know the correct way to, I don't know, quantify drift. So I tried an attempt. So we'll see.
Take a shot.
Yeah, shoot my shot here with the calculation. Okay.
Oh,
So
what should I look at?
yeah. Let's look at the LaTeX
Ready for LaTeX. Roger.
because yeah. Okay, so let's see. I put this little spiel here. Start with angular momentum conservation to find how much an object would drift from vertical when climbing a space elevator cable. We'll find the difference in speed between the surface and the mass at a height to then find the drift distance.
Okay.
Okay,
That's the plan.
so we're going to, I don't know if this is a good assumption, but I think it is, that the payload going up is essentially a free body. So we're going to use conservation of angular momentum to see how much the body, the payload, changes its angular speed, which would then become a driftward west
I see.
because its angular speed decreased.
Right. So kind of like if you're a figure skater and you have arms in versus arms out, you're extending the mass out, and so you'll slow down when you get further out.
Exactly.
Okay. Let's see how you do
Yeah.
that.
So I think we'll see how to do it. So we start with delta L equals 0. And the delta L is the angular momentum of the payload only.
Okay.
And then the 0 represents that it's free. There's no forces coming in and out, which is not true because of the cable. We're going to ignore that for now just to get how much drift would we have if the cable wasn't there.
So you're starting off with conservation of angular momentum, and you're saying there's no like friction, no external forces. Yeah, I'm with you.
Exactly. I guess there's no external torques, and the cable forces don't really give much torque because of the orientation of the forces. So pretty good assumption that it's 0, maybe.
Maybe.
Okay. So we got LF minus LI, so that's final angular momentum minus initial angular momentum.
Okay.
And yeah. And then we only care in the Z direction. We only care in a particular direction. We don't care about the other directions. So if the angular momentum of the Earth is along a certain vector, we only care about angular momentum of the payload along that vector. All the other angular momentums we can ignore for now.
So you're saying we're doing like an equatorial launch. We're not doing any like weird angle orbits around. Like, if here's the Earth spinning, we're going right around the edge. None of this like loopy stuff.
Exactly.
Okay.
And I think that's right because you'd build the space elevator at the equator because you get speed gains, I think.
Well, I mean,
that
also
right?
if you
Oh,
want it to
no, 'cause
be if you want it to be geosynchronous, and
that's right.
how do you do
Yeah, if you want it to be
geosynchronous on like a at like yeah, I think it needs to be the equator. Yeah.
I think it has to be the equator, otherwise you get weirdness. Yeah, I agree.
Yeah.
Okay, so then we plug in for L, which
Mhm.
is the simple formula is angular inertia times angular speed.
Okay.
Because we're only dealing with one direction now.
Yep.
Final minus initial. Okay.
Yep.
And then
Okay.
the final is okay. So the angular inertia of a single object is mr squared,
mr squared. Oh, of a point mass.
a point mass,
Okay.
which the payload is pretty good point mass.
Yeah, compared to the
I'd
Earth.
say.
Yeah, absolutely.
Yeah. So it's mr squared,
Mm-hmm.
but okay, let's go. Let's start with the initial one first, because that's easier to understand.
Okay.
So the initial angular momentum is mr squared, which would be the radius mass of the payload times the radius of the Earth squared.
Okay. Because it's launching
Times
from the
the
surface of the Earth. I'm with you.
Exactly. And it's launching at the equator.
Mm-hmm.
So the angular speed is 2 pi times a day, or sorry, 2 pi divided by the time in a day.
I see. So it's this many angles per the time interval, which is the same thing as an angle per second, which is angular velocity or angular speed, because we don't care about the direction. Angular speed. I'm with you.
Yeah.
Yeah, I like that.
So then the payload climbs the cable, climb.
Yeah.
And it is now, we're going to pick some point, a final point,
Okay.
which we will determine later,
Okay.
where it has climbed some delta r
I see.
away from the surface of the Earth.
So this is your placeholder for distance above the surface of the Earth.
Exactly.
Okay. And
So the
and it's
new
delta
angular
because it's
inertia-
super small compared to the radius of the Earth. Okay, I'm with you.
Yeah, I mean, it actually ends up not being super small, but we'll see. I made it delta r,
guess-
thinking it would be small, but
Placeholder for now is the key point.
Yeah.
Okay.
so angular inertia is mr squared. The new r is radius of the Earth plus the amount that it's climbed squared
Mm-hmm.
times the new final angular momentum, which that's what we want to calculate here. Is that omega
Angular-
final?
Speed. Yeah.
What did I say?
You said momentum, but
Okay, yeah,
angular speed. Okay. Yeah.
angular speed. Yeah.
Okay.
Okay, so now we're doing some algebra. Take the initial to the other side.
Mm-hmm. Mm-hmm.
And then I got some sirens. 1 second. Sirens.
Uh-huh. Miss that American siren.
Okay.
Mm.
Siren. Yes.
Feel the freedom.
Good siren.
I mean, it's effective. It got us to stop.
Yeah, I got to stop.
Yeah.
Okay, so then we're looking for omega final. So we divide by mr plus
This thing.
delta r squared.
Uh-huh. Bring it under. There it is.
Yep, there it is. And then cancel m.
Agree.
And then
Simplify.
once we cancel m, oh yeah, I bring the squared through. I did the FOIL in the
Oh,
denominator.
you're further. Okay, yeah. Okay, so
Yeah,
so
did the FOIL.
t goes to the bottom. R sticks around
Mhm.
2 pi. This stays in the bottom. Okay, then you FOIL it out. I like it. Okay.
Mhm. And then what did I write next? What we really need is the angular speed difference between the object at the Earth's surface once the object has climbed a distance delta r. So I think what I'm trying to say here is an object sitting on the surface at the equator is moving
Mm-hmm.
because the Earth is spinning.
Yep.
And then as the payload climbs,
Mm-hmm.
its angular speed is decreasing. So it's going to
Okay.
start to fall behind the object on the surface of the Earth at the equator,
Uh-huh.
which the person on the surface will interpret as a drift westward.
Yep.
I think. So what we really care about is the angular speed. We care about the difference.
Westward, because okay, if sun rises in the east and sets in the west, that's because we humans are rotating west to east. We're coming underneath the sun, which means if you send something up, if you're spinning away from it, then it looks like it's drifting to the west. Okay, yeah, I agree with that.
Yeah. Okay.
And so what you're saying is we don't actually care about the absolute angular speed. What we care about is the angular speed relative to the surface of the Earth. Because that's
right.
what you
In
see
fact-
as your drift.
Yeah. In fact, one step further than that, we care about the difference in linear speed.
Okay.
Because if I'm standing at the equator and I look up and I see the object is going to drift west, and I really care about how fast is that drift. Well, it's how fast am I going
Mhm.
versus how fast is it going. And the faster the difference in speed, linear speed in this case, the more drift west I'm going to see.
Wait. Can you? Your hands went off the screen. Can you do it again and lower?
Okay.
Yeah.
So, okay. So let's say so I'm on the Earth.
Yeah.
This is the Earth.
Yeah.
There's a person on the surface.
Yeah.
That payload. Payload. A payload climbs.
Headphones, yeah.
Right.
We're sending headphones to space. Yeah, good.
And send the AirPods to space. The surface has some linear speed this way. And then as the payload climbs, it's going to have a linear speed that way as well, but it's going to start to slow down.
Yeah. As the Earth is like rotating underneath it.
Right. So if it's rotating, it's actually the AirPods are going to fall behind.
Okay. I agree with you.
Yeah. Which on the surface of the Earth, the person is going to see this.
I see. Okay.